Finally, what do you think about multiple gap structure? Is it a consequence of the interaction in the of different species in K space or in R space, in real space, like you showed us these patches? What do you think? Which picture is more suitable to explain the experimental situation in uprights, for instance?
Thank you for this comment. I think this is the most difficult point to get from my presentation. And also for us was puzzling. That's why we did this kind of experiment. It is not important. This is the conclusion of 25 years. The quantum interference of the mixing of the exchange term is so complex that you can have enhancement in both cases. This is shown by the fact that if you take all cuprate superconductors, you have only 3 cases that are single crystals. Lithium iron arsenide, magnesium diboride, and yttrium 148. These are the only 3 single crystals. All the others are very complex matter, like with phase separation. Because you have a strain, you have the dopants, so it's phase separation. But the physics is the same. I think that to go to room temperature superconductivity, you have to control the complexity. Because if I go to mercury compound 160, it's very, very complex. With this nanoscanning technique. But it's the best. Lithium iron arsenide, that is a very good crystal, is not the best. The best are lanthanum oxide. Okay? So it seems that you have to control also the multiscale phase variation. Yeah.
As numerical simulation shows, phase separation is detrimental to superconductivity for a linear operation atoms. Therefore, the phase separation is not a friend but a foe of superconductivity.
Thank you very much also for this question, because we were considering this very, very well. This is not correct. If you say that you use the shape resonance, it's good. It's good because when you calculate the mixing term, you don't want hybridization. If the 2 pairs are in different space of the lattice, you suppress hybridization, and this makes the exchange term much stronger. I think I can find the paper by Kivelson where he said this works in such way, because he said always one yes or not in the same way. But what is right is in the single band is correct. But as you introduce the exchange there, I don't care if the boson, if the condensate are made by spin fluctuation. They can be both made by spin fluctuations. That's not important. Also, it can be triplet superconductor. That's not important. Important is the exchange between them.
If you have shown that the Fermi pairs and both liquid and you have interaction between these 2 species, then my guess is that it's sometimes too simplified, because when you consider bosons, it can be good for pairing or it can destroy the space, right? So, in some sense, it's only a general picture, but when you start to write down terms in Hamiltonian, it's a different process.
That's exactly what we've done. With Andrea Ferrari, we have used the schema of ultracold gases to consider the Bose DCS crossover in the perfect, without any approximation. You can read the paper. There is no one approximation. There is no one. If you do an approximation, you don't understand nothing. You cannot get the negative interference. sometimes they realized that there was also was a pseudo gap, but the pseudo gap is just anti-resonance because they don't calculate the fine-tuning of phase. And that's what I agree with you. The fact is that you have to do exact calculation. You cannot use this. This is a message of Fano, my professor. You have to do exactly the calculation of the phase of the wave functions. Not that's what states. Okay? So, and then when you see you have this drop and so on, and then the old Bose Kelvin model is completely over a completely new different scenario. I think Kagani is here, we can discuss this later. He completely agree on that. So
maybe I should make a short remark from the point of material science.
Yes.
About your complexity of system. There is very simple consideration. If you look at the Gibbs law, according to the number of phases and number of components, you will see that even for non-titanium copper oxide, in fact, it's a strict component system because the variable of oxidation states. And for these three component systems, it is not possible to organize even maybe two-phase state. Even you can immediately from this you can multi-phase state.
yeah.
So it's better in fact to study very simple compounds, not because increasing of your number of components, increase of number of coexisting phases. And the picture becomes very complex.
I agree completely with you. In fact, these materials show what the lattice structural transition, that was the idea of Mueller in 1986. They show structural phase transition and electronic instability that they spoke. They for both. That's why are soft materials. And these kind of soft materials can make the complexity very interesting, not bad.